Hi, I want to briefly review your virtual lab on equilibrium and Le Chatelier's principle and Q and K, because you will have a quiz on that. It's one of our learning targets, evaluating how a system will change to go back to equilibrium. And Le Chatelier's principle and Q and K are related because Le Chatelier's principle talks about how a system will return to equilibrium. So it's initially at equilibrium, then there is a change, which is called a stress to the system, and the system will then return to equilibrium by moving away from the stress. And that is really a subset or related to Q and K, because when we think about Q, those are our initial concentrations. So the difference between thinking about changes to systems and Q and K and thinking about them in terms of Le Chatelier's is when we think about them in terms of Q and K, we don't have to have a system that starts at equilibrium. When we think about Le Chatelier's, it has to start at equilibrium. But when we don't have a system that's at equilibrium, that's when we just go straight to thinking of the initial concentrations and how they compare to our equilibrium concentrations. So they're related. So this was our lab. I'm going to go through the cobalt system just as a review. And here we have our initial reaction. And you should have evaluated this data, and this looks purple to me. So my observations would be that it is dark purple. You should have written down the reaction, because that will help you. And so my observations related to it being dark purple would be, this would be my observations. The dark purple color shows equilibrium concentrations of both the reactants and products being present, because the products are red and the reactants are blue, which combine to make purple. So the purple color shows us you have both products and reactants present at equilibrium. Okay, so here's our first shift, and you can see that it changed to a dark blue. So your observation should have said that if you heated it, because that's this one, heat, it changes to dark blue. And so what is our explanation for why when we heat it, it changes to dark blue? And again, we're looking at our reaction here and noticing that our reactants are blue. So by changing to dark blue, we can see with our eyeballs that we have much less concentration of the products. We've made more reactants. So that should be our explanation. Here's an explanation. The change in color to dark blue shows a shift to make more reactants, which are blue, because they're blue, and less products, which are red. This can be explained by Le Chatelier's principle because the reaction is exothermic, it has heat as a product, and when it was heated, the reaction shifted away from the heat towards the other side to make more reactants. Since the system was at equilibrium and then we made a change, we can use Le Chatelier's principle to explain this. Keeping in mind, K is dependent on temperature. So by heating it, you actually changed your value of K. But you can explain the shift, and it's easy to explain shifts if you think of heat being a product. And so since we made more of this product, the heat, the reaction shifted away from the products. In this next example, we see that we had a system at equilibrium and we cooled it down and it became red. This is the new, what it looks like. And that red color implies that we now, in this new, when we've adjusted to maintain equilibrium, there are more products that are red than reactants. So our observations would be that it turned red. And the way we could explain that, this is how I would explain it. So here's an explanation. The change to a red color shows that the system produced more products, which are red, and reduced the concentration of the reactants, which are blue. This can be explained by Le Chatelier's principle, I abbreviate it, LOCP, because the reaction is exothermic, with heat as a product. And when we cool it, we remove the heat, so we're taking away heat, which means the reaction must shift to this side, the side to make more heat, and in doing so, it makes more of the products. Okay, so now we're going to evaluate what happens when we add water, and our observation should be that it turns red. But this is not because water is on this side of the reaction, because the equilibrium expression here is, here's the equilibrium expression. We have the cobalt water ion and the chloride, this is meant to be the chloride ion to the 4th power. I hope you can see that. But notice that water does not appear in this equilibrium expression because it's a liquid, it's pure. So changing the concentration of the water does not affect directly, I mean, you're not changing Q when you add water, but you are diluting everything. When you add water, you dilute the concentrations of everything. So this is a little trickier, and I want you to pay attention. Our observations are that the water turns red or pink. So what happens when you dilute everything, when you dilute a system, the equilibrium position is going to shift to the side that has fewer moles of your substance. And this will happen with pressure and with concentration. And let's think about this as we think about Q and K. So at equilibrium, when we were dark purple, this was our equilibrium expression. It equals a number, K. Now we've changed it. We changed it, and before it moves back to red, or these are our new concentrations. So we've changed it, and this is immediately after the change. And we have, let's pretend we diluted it by half. So we added twice as much water. So then our concentration of our cobalt water ion is going to be 1/2 what it was, and our concentration of our chloride ion will be 1/2. And our concentration of our cobalt tetrachloride ion will be 1/2. But mathematically, what we're doing here is, if I were to take the 1/2s out of the expression, this is 1/2. This right here is 1/2 to the 4th power, which is 1/16. Oops. And then that would be multiplied what we had originally up here to the 4th, and down here we have 1/2, and then we would have what we had originally down here, the Cl4 minus 2. So these 1/2s cancel, but you can see that this expression is different from this one because it's the numerator is 1/16 of what it needs to be. So because the coefficients are powers, and because you have more than one, in this case, more than one product, when we dilute it, the products are affected more by the dilution than the reactants. And that's because there are more moles on the product side than there are on the reactant side. So in order to make this equal to that, we have to make more products to get this number up again. We need to get the numerator up again, so it's going to be equal to what this was. So this is how you could explain it when Q versus K. When you dilute everything, the Q is going to be affected much more on the side that has more moles. And so it will shift to make more of whatever is on the side with more moles. Now, if the moles are equal, there won't be a change. So how would we explain this? So this is how I would explain this. Because the entire system is being diluted with water, the system will shift to make more of the side that is affected more by the dilution. That will be the side with more moles. So in this case, the system will shift to make more of the products because it is the side with more moles. Okay, we're only 2 more to go. In this case, we're adding the, wait, did I skip one? Silver nitrate. This is adding the silver nitrate. And our observation should be that it turns red. And also, we have a precipitate here. We have a white precipitate. And you might have said bubbles, although I actually think these are meant to be the precipitate that's forming, because I don't see a lot of bubbles at the top, or a lot of fizzing at the top. So I think this is just the formation of a precipitate and a change in color. So that would be your observations. And how would we explain this? Well, we're adding silver nitrate. So I'm going to put it up here. We've added silver nitrate, and silver nitrate in water is going to become the silver ion that's aqueous and the nitrate ion aqueous. Anything that has nitrate is completely soluble, so it will split up into ions. So we're going to add that over here. Nitrate. And nitrate ions are always soluble, but silver and chloride, when you put them together, that becomes insoluble silver chloride. So this is going to create a side reaction. The chloride's going to combine with the silver and form silver chloride solid. And that is what we're seeing down here. This is silver chloride. So you need to know for this, or look it up, that there is a precipitate forming and it's silver chloride. And so when the chloride reacts with the silver, we are reducing our chloride concentration. So that is why this reaction, so there's a side reaction going on. It's the silver plus the chloride makes solid silver chloride. And so that reduces our chloride concentration. So this reaction has to shift this way to make more of the products, which is why it turns red. So how would we explain that? So because the silver ions react with the chloride ions to form insoluble silver chloride, the concentration of chloride ions, a product, is reduced. According to Le Chatelier's principle, the reaction will shift to the right to make more products. Or you could say, in order to have Q equal K, the reaction will shift to the right to make more products. Either one. And finally, our last one. And here we're adding potassium chloride. And so potassium chloride will also, if it's a solid, when you put it in water, break up into aqueous ions, potassium and chloride. And so we're adding chloride ions here. So we're increasing the concentration of chloride ions. Right? Right. I think I have the wrong picture here. No, I have the right picture. We're increasing the concentration of chloride ions, and we can see our observation would be that the reaction turned blue, meaning that it shifted to make more reactants. And that makes sense because we've increased the concentration of a product. So according to Le Chatelier's principle, it's going to shift away from that increase to the other side of the reaction to make more reactants, or to make Q equal K again. And that is the end of the lab review. I'm going to post a video going over some new material that you have to know. The end.